Welcome to the LemnaTec Academy. In this video, we will create our first image analysis. This will be a simple one using only well-behaved example images. Nonetheless, we will demonstrate some basic concepts of image analysis with LemnaGrid. So let's get started. Let's start with our first analysis. As a preparation, I have done a few steps outside this video. I selected some example images. These must be representative of what one expects to see with the experiment you want to analyze using this analysis. These example images should not be too few, but neither too many, as too many may slow down the development process too much. The number should range between 3 to about 10. It must include a few normal examples, but it doesn't hurt to put focus on the extremes. That said, we will start the development with just one or very few example images, say up to 3, and use the others later to fine-tune the analysis. You can use LemnaExperiment for the selection. Save the snapshots containing images you identified as example images somewhere on your local disk. This is what I have done in preparation for this video. An image analysis consists usually of two parts. The segmentation part detects in the images where the objects of interest are. This might be leaves, whole plants, buds, roots, you name it. Often this is the more challenging part, in particular with RGB images. Once we have identified the objects, we can start getting measurements of them. Many of these are executed automatically by LemnaGrid, but sometimes this can be more difficult. For this video, we will stick with a simple case. We start with the usual minimal default analysis. The first thing is to load the example image. We open the Disk Universal Reader configuration and load an example. This is our first example. Then we need to do the segmentation. There are a couple of options to do this. I already demonstrated one option in the last video, but in this video I opt for another one. We use a device called color threshold. The advantage of this device is that it has a simple and easy to reproduce way of segmentation, which is easy to report in publications as well. With this device, we select all colors within a certain range of values to be the foreground. Foreground is another way of saying these are our objects. You can do this in the normal RGB color space. Let's say all pixels where the red and blue value is smaller than 128, and the green values are greater than 128. That does not work very well. But RGB is not the best color space to work with here. I recommend to use HSV or LAB. Since LAB is harder to understand, we will use HSV in this video. By the way, what is a color space? Colors in digital images are represented by numbers, obviously. The camera records the images as values of red, green, and blue. This is the RGB color space. However, one may convert these numbers into representations of the same color which are easier to comprehend, or have some technical benefits in certain contexts. These alternative representations are called color spaces. LAB and HSV are such color spaces. The advantage of LAB is that it was designed to mimic the human perception of colors best. Therefore, if you take the distance between two colors in LAB, it should be close to what humans think it should be. This comes at the expense that the values of LAB are not that easy to understand. This is different with HSV. It represents colors in terms of hue, saturation, and value or brightness. Value or brightness is pretty self-explaining. Saturation, if the saturation is lower, then the color is more grayish, and if it's higher, it's less. The hue finally represents the bare color from red to green to blue and back to red. It is usually represented as an angle between 0 and 360 degrees. In LemnaGrid, we have a step width of 2 for the hue. All other values are represented by values between 0 and 255 in LemnaGrid. A hue of 0 degrees is pure red. A hue of 120 degrees is pure green, and a hue of 240 degrees is pure blue. So if we select a hue between 0 and 180 degrees, we select basically all greenish colors. We switch to HSV and select 60 to 180. This looks almost perfect already, but at a few places we missed the plant. Let's zoom in on this location. If you hover the mouse over the image, you will notice two things. On the right, we have a crosshair, which is following the mouse on the left image. And if we press Ctrl, a tooltip tells us the color at the position of the mouse. This color is given in RGB and the selected color space, which is HSV at the moment. We see that the hue value at the missing parts is below 60. They are looking more reddish. I like to include them, so therefore I lower the bound for age to 30. This is better, but not perfect. Let's try 20. That's better now, so we keep the setting. You may have noticed we added in the last steps also a few false detections in the area of the soil and the pot. Sometimes these are unavoidable. We can deal with them in a subsequent step, as you will see. On the other hand, this demonstrates why it's important to prepare your samples properly. You should not use wooden sticks to stabilize the plant. Use something blue instead. It makes the segmentation easier, and you won't need to do too much of a compromise. The same applies for the soil and the pots. Use black soil in pots if possible. Okay, we are done here. Let's move on. As we had some false detections in the last device, we need to tidy our result image. For this, we use two filters. First, the multi-step morphological. With the morphological filter, we can add and remove pixels from the edges of the foreground areas. In order to get rid of the small false detections, we first remove one pixel and then add it again to preserve the original shape as much as possible. This removes all small detections which are no thicker than 1 pixel. We have reduced the false detections but not removed them, so we could use -2 and +2. This looks better, but not perfect. The larger the filter settings, the more the shape of the actual object is changed, so we leave it here at 2. The second filter is called Fill Areas. It fills all areas, foreground and background, which are smaller than 20 pixels in size. However, the default value of 20 is rather conservative. We still have some false detections. We could try 200. And this looks really good now. Now we are finished with the segmentation part. In order to continue, we need to convert the binary foreground-background image into an object list using the universal converter. We are almost done. Since LemnaGrid calculates the morphological parameters automatically, we don't have to do anything else for the measurement part except organizing to save the results. This is done by the objects writer. Every time we drag a writer on the canvas, we need to give the output a name. This name will be used as prefix to the different parameters in the result table. You may have multiple writers in your analysis, but this is a topic of a later video. We connect the lower input to the output of the universal converter. This port requires an image object list as input. On the second input, we shall connect the original image or a derivative of it. In order to keep things tidy, I add a loop through device as a diversion. Let's open this object writer device. You remember the folded section at the side of the images I mentioned in the last video? This becomes important now. This image has two layers, each of which has a control section here. The section opens if we click on it. Right now we want to work with the object list out section. We configure here a couple of things. How the objects are represented in the image. By the border of different widths, bold, extra bold, by filling the object, or by filling the background. Let's stick with the contour. We can also select the color. Let's select some light green. We can also choose rainbow color. In this case, each object in the image gets a different color, which can be useful if you have multiple objects in one image. But we have just one, so it doesn't help us. In the second section, we can add a graphic representation of certain morphological parameters, such as convex hull, bounding box, caliper length, etc. Let's choose convex hull and bounding box and use extra bold to draw it. We could also change this color here. Below this, we have a list of parameters which we could add to the tooltip. Let's try compactness, convex hull, roundness, and size. If we move now the mouse over the object while pressing Ctrl, we see the values of these parameters of the objects. The parameters in this list are essentially those which are written to the database. You find the list of them in the device description below. Please note, not all of these parameters are present by default. Some of them need extra devices in the grid to be filled with reasonable values. For example, the color-related parameters. We will cover this in later videos in more detail. Defining this image is not just for viewing pleasure. Each writer creates not only the data table, but also at least one image to represent the analysis result. Here you define how this image will look like. Do you remember? In the beginning, I said we should not base our analysis on just one image, but multiple images. So now's the time to add more images to the analysis. We open the reader again. In the parameter section, you might have noticed the simple Add Advanced tabs. In the Advanced tab, we can add multiple images to this reader. We can now switch through these images using the controls at the bottom. Let's have a look into the areas again. We can switch through the different images and their results here again. This looks pretty good, but you may have noticed that in some of the images, we again have false detections. We can solve this by increasing the area size to 500. This looks good. Let's have a look at the final result. This looks really good, but I selected some easy images for our first analysis. But if you prepare your samples carefully, it can be that easy. However, 4 example images are still not a lot, but it's enough for this demonstration. Finally, we have to save this analysis to a file. And so we got our first basic analysis. This should provide you with an idea on how image analysis with LemnaGrid works. It shall give you a hint where you can optimize your sample preparation in order to get an easier image analysis. An easier image analysis means usually a more reliable and robust one as well. This is the end of class 2 of our software training, at least for now. We may add more videos here in the future as we add software features which are relevant at this stage. We will continue the software training in class 3, where we will tell you more about creating analysis with LemnaGrid and how to integrate them into the workflow with LemnaExperiment. See you there.